right, so this is the one about moonshine. That first organic molecule is ethanol. Didn't mean that you would second guess that. It is just ethanol. And there's ethanol and water in the feed. Okay? So, trying to go to the logic of solving the problem. Okay? I almost always make an assumption about the feed. I know some of you don't go about it that way. I almost always do. Okay? What kinds of assumptions could we make in this problem? Yeah? I can assume 1 mole of ethanol in the feed. And if I do that, what do I have to do in order for the solution methodology to continue to work? What would I assume about the water that was in that feed? Good, trick question. You don't make an assumption about the water because that's what you're asked to find. Okay? So yeah, I could make an assumption about the ethanol. Leave the amount of water that came in as a variable. That's not the fastest way. Why isn't that the fastest way of going about this one? What do I know about the airstream? It's 15 or 20 times the amount of moles, not of ethanol, but of ethanol and water mixed. So the faster way for me to do this one is to say, hey, let's make it 100 moles of shine. I don't know how much of it's ethanol. I don't know how much of it's water. But if I assume it's 100, I know exactly how much air is coming in. So we can actually do it both ways. I've never done it just assuming the ethanol part. Literally never. But it uses all the same tools. So I'll show you the way I did it. Then we'll do it again using that assumption. Okay? And I'm going to let XE be the mole frac ethanol. Another big thing, all the ethanol reacts, which means the approach where I assume the amount of ethanol is going to be very powerful because I'm going to know exactly how much it reacts. It's going to put the variables in a different place, but it tells me an awful lot either way. So I've said before, I think, that if you spend a lot of time trying to figure out which assumption to make, you're probably burning time that you shouldn't. I said, hey, this is the easier way of doing it. It's the first way I saw it do it. If you saw the other way, you should pursue that. And as fast as possible. Okay, so if there's 100 moles of shine coming in, there it is. Okay. My ethanol balance is going to look like this. The N is going to be the 100 moles of shine times the fraction of them that are ethanol. The consumption term is going to be exactly the same. Which means this now becomes my stoichiometric key. The oxygen there's 100 moles of shine. I was told there was some factor, either 15 or 20, and it's 21% of that is oxygen. And then I just do the stoichiometry between my stoichiometric key and oxygen. care of my inert. The same 100, 15.21, oh, sorry, 0.79. Get out of here. Remember, the ratio between oxygen and nitrogen is known at the inlet, not the outlet. So I'm looking at that inlet term for oxygen, not the combined term that I wrote down, which represents the amount of oxygen out. CO2, out is gin, which is just stoichiometric from my consumption term. Same with water. Oh, except, I almost did it too. Don't get it twisted, I can make mistakes as well. The inlet is everything that's not ethanol from my moonshine feed, and then the stoichiometric based on that consumption term. Now I'm kind of a weird guy. I should have probably just totaled up that ethanol to say there's 0 there. But I really like how 100 XE coming in and 100 times 1 minus XE here in the water end gives me back the 100. So I got 100 moonshine, 1500 air, and then plus the 100 XE. And when I write it that way, it looks really nice. It makes like a lot of sense to me. I get all the shine, all the air, and then I'm generating a few moles because on the left-hand side of my chemical reaction, I got 4 moles, and on the right, I got 5. The number gets bigger the more reaction I do. You were given a mole fraction of water. And there's only one unknown. Let's try and do it the other way real quick. Like I said, I've never done it that way, but let's assume 1 mole F. I'm going to represent the oxygen, I'm sorry, the water then, with a big old B. So my ethanol balance, stoichiometric key. I might like this approach better.
Unless I did it before, they like to move on. So, no, they like
Let's see. The oxygen part. We know the amount coming in, that's going to be 21% of the air. And then the consumption is 3. Okay? The nitrogen part. generation terms. And then the water. If I sum all this up, let's see. I've got 15 times 1 plus b plus b plus 2. The water, total. It's still one equation and one unknown. I'm going to hope real hard the algebra works out to the same sort of answers. The only possible drawback here is that after you calculate B, you've got to then calculate the mole fraction in the feed. 1 plus B being the total amount of shine. One extra step. If this is the way you saw it, it can work. I'm very talented. All right, the long one with lots of words. I want you to look for a second at the second reaction. Of all the things that are in the first reactor, either fed to or coming out, which, if any, are involved in the second reaction? Only H2. Which means when you were given a ratio for CO2, what happens to CO2 in the second reactor? Nothing. I don't even have to think about the second reactor to do CO2. What happens to water in the second reactor? Nothing. All right, so I'm going to make an assumption here. I think the only one that would make any sense would be the amount of methane coming in. Don't know that anybody else would do anything different except maybe try and assume something at the outlet, but there's not that much information about total stuff in the outlet. So I'm not sure that I would go that way. But I do not know how much CO2 is coming in with the methane, and I do not know how much steam is being fed. information about the intermediate stream. Should have been real fast to figure out how much of the methane was reacted. Every other part has a ratio for how much methane is in the outlet from the second reactor. Remind me, what happens to methane in the second reactor? Nothing. How much methane is going to come out of the second reactor? 2. I already know half of every ratio that I was given. Second part is about CO2. CO2 is inert in every reaction. So the amount coming out is only what's coming in, which I represented with a big old B. So if B is the amount of CO2 that came in with my biogas feed, I assume 10 methane, 2 CO2, 12 total. 10 out of 12 is methane. In part B, I was given information about water. Water's coming in as steam. I don't know how much. And it's being consumed in that first reaction. 1-to-1 with the methane. Oh wait, we already found out that's 8. So CH4 to water. Total moles of biogas coming in, 25 moles of steam. You can really quickly find the ratio. For the last part, it's the only one that involves that second reactor. Look at my hydrogen balance because I know all of it that gets generated gets consumed. 8 moles of methane are being reacted. 1 to 3 generation of hydrogen. Don't know how much nitrogen I'm getting from the air, so I'll represent the nitrogen that is fed as a big N. The consumption of nitrogen, now that I know the consumption of hydrogen in the second reaction, it's just stoichiometric. And I'm given the ratio of CH4 in the outlet to nitrogen is 1 to 8. We know the methane part is 2. silicon one. I believe in both. 500 grams per minute were being deposited. If you know how fast one of the things is getting generated, you know everything there is to know about the reaction. I know the consumption in order to make that silicon is going to be 8.3 moles per minute. It's 1-to-1 the silicon dioxide. What do I know about the silicon coming in? Not that much. Can't make any assumptions because any assumption would break the information given about 500 grams per minute being positive. So I won't make an assumption. I'll just represent it with a variable. What about the oxygen? Yeah, can't really say anything about the oxygen either. But I know a lot about the consumption term. The nitrogen being inert. So I've really got two pieces of information that I can use. One's about the total amount of inputs. And the other one's about mole fractions in the output. Notice how nicely that fits in there. All right, we're past time. It'll be a new problem on Wednesday. I haven't written it yet. Hopefully it'll be about 20 minutes. Don't know how many points it'll be worth. Find me if you need me. And thanks a lot for the feedback, guys.